A truck with thin tires looks odd, doesn't it? It doesn't look like it can manage the load it's carrying. As we've all seen, trucks need wide tires. On the other hand, let's look at a housewife trying to chop vegetables with a thick, blunt knife. She's not having much success. To chop efficiently, she needs a knife with a sharp blade. What is the significance of the width of the tires and the sharpness of the knife in these cases? This can be explained through the concept of thrust and pressure. The truck needs wide tires to reduce the pressure of the cargo. The knife needs a sharp blade to increase the pressure exerted on the vegetables. In this lesson, you will learn about thrust and pressure, with special emphasis on thrust and pressure in liquids. At the end of this lesson, you will be able to define thrust and pressure, differentiate between thrust and pressure, calculate thrust and pressure in given situations, explain the effect of pressure exerted by fluids, derive the expression for calculating pressure in fluids, state Pascal's law, and explain the applications of Pascal's law. Thrust is a vector force acting normally on a surface and is denoted by F. For example, consider the simple act of driving a nail into a wall with a hammer. The force that you exert on the hammer during this activity is thrust. Thrust is measured in dyne in the CGS system, and Newton denoted by N in the SI system. We have seen that nails have pointed tips to help us drive them into surfaces. Why is it important for a nail to have a pointed tip? For that matter, why is it important to have a sharp knife to chop vegetables? The force you apply in driving a nail or chopping vegetables is translated into pressure, depending upon the surface area of the object on which the force is applied. In other words, pressure is the amount of thrust acting on a unit area. Pressure is denoted by the letter P. Hence, pressure is calculated by dividing thrust with area. The lesser the surface area of an object, the more the pressure applied by that object. The pointed tip of the nail minimizes the surface area of the nail on which thrust is applied. Therefore, while driving the nail into the wall, the pressure of the hammer is maximized, which helps drive the nail into the wall. Pressure is scalar and is measured in dyne per centimeter square in the CGS system, or Newton per meter square or Pascal, denoted by PA in the SI system. Another example will help illustrate further the distinction between thrust and pressure exerted by a body. Take a piece of foam and two identical metal blocks, say A and B, weighing 300 grams. The length, breadth, and thickness of these blocks are 30, 20, and 10 centimeters respectively. Place the metal block A vertically on the foam and the other iron block B horizontally. Now let's compare the compression of the foam where blocks A and B are placed. The foam shows more compression where the metal block A is positioned vertically. Considering that both the blocks have the same length, breadth, height, and weight. Why do you think we see this difference in the compression of foam? This difference can be attributed to the difference in pressure exerted by each block. Block A was placed vertically over the sheet of foam, while block B was placed horizontally. The surface area of block A in touch with the foam is 200 square centimeters. On the other hand, the surface area of block B in touch with the foam is 600 square centimeters. Using the formula for pressure, we can now calculate the pressure of blocks A and B on the foam. The pressure of block A on the foam is 1,500 dyne per centimeter square. The pressure of block B on the foam is 500 dyne per centimeter square. Thus, in block A, the same thrust was acting on a smaller surface area. Hence, the pressure exerted by block A was higher. This explains why the foam showed more compression where block A was placed. The thrust exerted by a body remains constant, placed in any position. However, the pressure exerted by the body changes with a change in positions. Let's look at another everyday example. You may have used chairs in which the seat is created from plastic wave. These chairs are quite safe to sit on. However, if you try standing on such a chair, the plastic wire may give way under the strain. This is because when you stand on the chair, the area of contact becomes much smaller, and the pressure on the wire crosses the safety limit. In both the cases, the weight of the man, that is the downward force acting on the chair, is the same. However, the area on which it is acting has changed, leading to change in pressure exerted on the seat of the chair. So far, we looked at the examples of thrust and pressure in solids. However, thrust and pressure are equally applicable to the other states of matter, liquids and gases. Liquids and gases are collectively referred to as fluids. Since all fluids have the tendency to flow, like solids, fluids also have weight, and this weight exerts a force on the walls and base of a container. We can demonstrate the effect of pressure in liquids through a simple example using a plastic bottle. Fill the plastic bottle completely with water. Then make a small hole in the lower half of the wall of the bottle. You will see that the water gushes out through the hole with considerable force. This force is due to the pressure of the fluid at that point. So, how do we calculate pressure in fluids? To derive an expression for pressure in fluids, let's consider a beaker filled with a fluid, say water, of density D, to a height h. Drop a coin with the area of cross-section A into the beaker. The volume of the water column above the coin V is equal to area of cross-section of the coin multiplied by the height of the water column. This gives us equation 1. Volume V is equal to A multiplied by H. The mass of the water in column M is the product of the volume of the water and its density. Thus, M is equal to V multiplied by D. Substituting equation 1 in the expression for mass, you get equation 2. That is, M is equal to product of A, H and D. As you know, weight of a substance is a product of its mass and the acceleration due to gravity, G. Therefore, weight of the water column, W, is equal to the mass of the water column multiplied by G. Thus, W is equal to M multiplied by G. Substituting equation 2 here, you get equation 3. Weight of the water column acts normally on the object. Thus, the pressure P acting on the coin is the ratio of weight of the water column to the area of the coin. That is, P is equal to W divided by A. From equation 3, we know W is equal to product of A, H, D and G. This gives the expression of fluid pressure P. P is equal to HdG, where H is equal to height of the water column, D is equal to density of the water, and G is equal to acceleration due to gravity. Using this expression, you can calculate the pressure applied by a fluid in the walls as well as the base of a container. The pressure at a point in a fluid is equal in magnitude in all the directions. Now let's look at some applications of the concept of pressure in our everyday life. You may have seen a warning at the back of trucks moving on highways. Caution! Air brakes maintain 50 feet distance. So, air is used in applying brakes for these huge vehicles? Amazing, isn't it? In fact, the hydraulic brake system used in cars also involves usage of a fluid brake oil. Both these applications, air brakes and hydraulic brakes, are based on a law related to pressure. This law is called Pascal's law. Pascal's law states that a change in the pressure of an enclosed incompressible fluid is conveyed undiminished to every part of the fluid and to the surfaces of its container. Let's conduct an experiment to verify Pascal's law. We take a container with two openings of unequal cross-sectional areas. We fill this container with water and then close the openings with airtight pistons, 1 and 2. Then we push piston 1 inwards. As piston 1 is pushed inwards, piston 2 moves outwards. Thus, the increase in pressure through piston 1 is conveyed undiminished through the liquid to piston 2. As the area of cross-section of piston 2 is greater than that of piston 1, the thrust exerted on piston 2 is greater than that on piston 1. Hydraulic brakes as well as air brakes operate on the same principle. Let's see how this principle is applied in the construction of hydraulic brakes. A hydraulic brake system consists of a brake pedal, a piston, a master cylinder, 4 hydraulic lines, 4 brake cylinders, 8 brake pistons, 4 wheels, 4 restoring springs. Now let's see how hydraulic brakes work. The master cylinder and the brake cylinder are connected to a thick copper pipe called the hydraulic line. Thick brake oil is filled in the master cylinder and the brake cylinders, and they are fitted with airtight pistons. The master cylinder is connected to the brake pedal. A brake cylinder is connected to the metallic rim of each of the wheels. Now let's see how this arrangement of hydraulic brakes works to enable a driver to stop a car when driving. When the brake pedal is pressed, the piston in the master cylinder goes in, forcing brake oil out with some pressure into each of the brake cylinders. At each brake cylinder, two opposed pistons attached to brake shoes are forced outwards. The outward movement of brake shoes presses the brake bands against the inner surfaces of the wheels to stop their rotation. When the brake pedal is released, the restoring springs at each wheel restore the pistons to their original positions. Thus, hydraulic brakes in automobiles employ the concept of pressure to enable drivers to stop heavy vehicles by applying a relatively light touch on the brakes. This brings us to the end of the lesson on thrust and pressure. In this lesson, you learned about the concept of thrust and pressure, the expression to calculate pressure in a liquid, and applications of thrust and pressure. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard.